Hello everyone, this is Experiment Designs in Computer Science week 5. And this week will be a little bit different from the other weeks because we're not going to introduce new material. We are going to do an R tutorial and we are going to do a review on the reports that you sent last Monday. So let's get started. So first, I want to start with comments and the general outline for this week. So this week, we are going to focus on examples. The first video, not this one, the next one, will be our tutorial by the TA Yuri. And then there will be a second video or maybe a few more doing analyzing a case study. This video that you are watching right now will be a response to the comments, the survey comments and the survey questions as we do every week. And about the reports, I'm still grading them. I got about 36 reports. So when I finish grading the reports, I will do another video still in this week describing my general impressions, general comments about the reports. So stay tuned for that one. Now, talking about 36 reports, I got 36 reports, but on average, there are only 32 people answering the attendance surveys. Remember that the attendance surveys, they will count for the attendance of this course. So don't forget to reply to the attendance surveys. If you don't have enough attendance, you will not graduate on the course. Okay, now let's go to the survey results. The first question I asked, let's start with something like, the first question I asked on the survey was your favorite animal. We got 14 people voting for cats. Very good. And 10 people voting for dogs. So obviously cats are more favored than dogs. 3 people got wolves. So we got Arctic wolves, regular wolves, man wolves, many different kind of wolves. And then we had a few more animals here. All these animals had 1 vote each. We had penguins, pigs, panda, turtle, hedgehog, prairie dog, hyena, rabbit, bird, horse, and meerkats. Unfortunately, we did not have any arthropods. I'm kind of sad about this and disappointed on you. And the person who voted for pigs said that the pigs is the favorite animal because they are tasty. All right. So now let's go to the experiment question. So I did 2 theoretical questions for you in this in this survey. The first one was to give an example of a paired experiment. We got about half of the people got the answer correct and half of the people got the answer incorrect. To be quite honest, those that got the answer correct, I feel that maybe you understood the answer, but you could not quite explain it. And the main idea, when you try to explain a paired experiment, you have to think about what is the experiment paired on. Okay, so you can say an experiment paired on the type of car, or an experiment paired on the algorithm, or an experiment paired on the people who are answering. So every experiment analysis that is paired on something, and if you can identify what this something is, it's easier for you to understand what is the paired experiment. Okay, for example, I'll give you 2 examples of correct examples that I find really good. One that I found very interesting was someone that said, oh, I want an experiment that tests the execution time of many different algorithms that are implemented in different languages. For instance, we have algorithms implemented in C and algorithms implemented in Python. And we compare, for example, deep first search algorithm, we compare Dijkstra algorithm, we compared the prime sieve algorithm, and obviously each algorithm will have different running times. So the difference of running times in the algorithm might be bigger than the difference in running times of the language. So we want to pair this experiment on the algorithm to make sure that we remove the influence of the difference in running time from the algorithm. Okay, so that was a very good example of paired experiment. Another that is very general, and I think it's a very good example as well, this was suggested by many people, but I can summarize it as panel testing. What is panel testing? Panel testing is when you have a number of people doing evaluating something. So the traditional example is if we have like different foods and you have 5 people eat the different foods and give grades for them. For example, different kinds of coffee. Now it's the same people grading the different kinds of coffee, so the experiment is paired on each person. Okay? By the way, when I say the word paired, do not think of pair as 2 people linked together, because you may think of 2 different people. And that's not it. The idea of paired is that the experiments are linked by a common denominator. So in the case of the panel, the observations are linked by the same panelist. You can have 2, 3, 4, 5 observations, and if they are linked by the same panelist, they are paired on the panelist. In the case of the algorithm, the observations are paired on the algorithm. So you have the same algorithm implemented in different computer languages. So you can have 2 C and Python, you can have 3 C, Python, and Java, you can have more. So paired is the link that links all the observations. I know that pair, we think about 2 things, but try to understand this time that the word means something a little bit different. Okay? Now, there were some common incorrect examples. So, for instance, there was one example that compared students who go to cram school and the students who don't go to cram school. Notice that the problem here is that there is no clear link between the students that go to cram school and the students who don't go to cram school. Maybe you could specify that the students must be from the same family, but that's a little bit pushing it. But that's the thing. If you cannot explain what is the link between the observation, it's hard to say what's the pairing. One person said, oh, I want an experiment that is the melting speed of different brands of ice cream. Okay, but what is the link? What is the pair? Okay, the idea of a paired experiment is that you have an explicit, a clear pair, an explicit pair. Okay, another student said Mendel's experiment, and again, of course, yes, Mendel did many famous experiments, but if you don't say what was the paired, what was the pairing, what was the link between the observations, how can you know if the experiment is a paired experiment or not a paired experiment? Okay? There were a few that were technically incorrect that I want to talk about. One student suggested an experiment where you have the same data set, you have several data sets. You have one data set that is the same. You compare 2 algorithms on the same data set, and you do the computers, you run the 2 algorithms on different computers on different hardware. And at first, yeah, this is okay, but why are you comparing on the computers on different hardware? And you have to think about it carefully, because if the computers have very small difference, then the pairing may actually hide some natural variation. If the difference between the computers is smaller than the difference between the 2 algorithms, maybe you are not really controlling on these differences. On the other hand, if you're doing something like supercomputing, where the difference in architecture makes a very big difference on the performance, then yes, this example would be correct. So, of course, you always, and this is very important, you always have to think about the condition of your experiment. Okay, there is no general answers in here. Now, another student suggested comparing the average of men and women's salary. Again, as I said in the beginning, for you to say that an experiment is paired, you have to say, what are you pairing on? For this experiment is interesting because depending on the experiment design, we can create a paired experiment or an unpaired experiment. For example, it could be unpaired if we choose 1,000 men from Japan randomly and 1,000 women from Japan randomly. So that would be random observations, and we measure the average of the salaries. So in that case, it would be an unpaired experiment. And you probably would not be able to get some very good data from that. it would be very mixed. There would be variations because of job position, variations because of age, and many other variations that would make your conclusions kind of muddy. On the other hand, one experiment on this theme that was made many times was a comparison of salaries paired on job type. So you get a man engineer and a woman engineer, a man surgeon and a woman surgeon, a man assistant professor and a woman assistant professor, and then you do your experiment based on the job. In that case, yes, that would be paired. It's an experiment paired on the job. Again, every experiment that is paired on something. Okay? So I think this one is like the answer was limited because the answer the student gave was only this, but it could be a very good answer if you gave a little bit more detail. So that was the first question. Give an example of a paired experiment. Now, the second question of the survey. The second question of the survey was difference between one-tail and two-tail experiments. And I found this one very interesting because, as I said in the survey, I did not explain this in class. So your task was to look, study it, and give your answer. And the majority of people, as you can see here, the majority of people gave correct answers. Some people gave incorrect answers, but I think that about half of the people that gave incorrect answers, maybe they could just improve their explanation a little bit for the answer to be correct. So just to summarize the explanation, I think almost everyone got this correct. One-tail test and two-tail test are basically the same test, but with some variations of the design. The variation is the number of rejection regions. In the one-tail test, you have the null hypothesis that two quantities are equal, and the alternative hypothesis is that one quantity is smaller than the other, or that the one quantity is bigger than the other. So it's one direction. You're comparing towards one direction, towards greater than or towards less than. Talking a little bit more mathematically, because you have in two tails, you are comparing equal or different. So in two tails, the rejection region is bigger than a certain value or smaller than a certain value. And because you have two critical regions, you have to divide the size of each region half to have the same confidence. Okay? In mathematical terms, the alpha of the test is divided by 2. Half of the alpha goes to more or equal, and half of the alpha goes to less or equal. Okay? Another way to think about it is that two-tail tests will require stronger evidence for a rejection because the rejection region is smaller. Now, we have some questions from the students. So first, the first question I got from the general comments was, I would like to ask about statistic test parameters. What do you base on while deciding the 3 parameters: significance level, power, and meaningful difference? And that's a very good question. It's very good that you asked the question. And in general, the first thing you have to do is to think about why are you doing the experiment. Okay, so when you think about why you are doing an experiment, you're going to have ideas that will help you answer these questions. Okay, here are some general ideas, general rules of thumbs. About the significance level. The significance level means roughly the chance of a false positive in the experiment. Okay, in general, people use 95% significance. That's like the standard value. But of course, this can change depending on the situation. For example, if we think about particle physics, in particle physics, the standard is much higher. They use 90-99 confidence or 90-99 confidence. They do that because they do many experiments with particles, and there is a very high chance that you have a false positive because of an error in the sensors, or because some noise in the, and they want to reject that because if they accept that false positive, they will have wrong basis, wrong data to assemble the physical laws that they're studying. In computer simulated experiments, we have a situation that's a little bit similar. in computer simulated experiment, it's cheap to obtain observations. You can just run the computer more. Because of that, we might want to use a more strict value, such as 99%. Also, if the cost of a false positive is too high, in other words, if when you get a false positive, something really bad happens, you might want to increase your significance level. For instance, we can think about drug safety testing. That's a situation where it's very bad if there's a false positive, so you want to increase your significance level. Okay? Now, we can look at it at the other side. We can want to use a smaller value. Okay, we can want to use a smaller value of significance. But for example, if the experiment is very hard to do, so you cannot have many repetitions of the experiment, and if there are a lot of noise in the experiment, and when does this happen? This happens a lot in experiments that involve human interviews. These experiments, it's very expensive to interview many people, and there is a lot of noise because people have very different opinions. So in this case, we might want to use a lower significance, such as 90% or even 80%, to account for the extra noise in the experiment. Okay? Now, the power level is similar to the significance level in the sense that the accepted value depends on the situation. Okay? Different from the significance level, we cannot really control the power level, as we discussed in the lecture number 3. So what we usually do is that we use the power level to determine if the experimental design should be changed entirely. Values around 80 are generally considered acceptable power, but sometimes even a lower value can be also accepted. Remember that power level is the probability of a false negative. A false negative is usually less critical than a false positive when we're talking about experiments in computer science. That's why it's acceptable to use slightly lower power levels. Now, the meaningful difference is a little bit harder to talk about because it depends entirely on your application. For computer applications, in general, we are proposing a new algorithm. And a new algorithm is usually more complicated than the existing algorithm. If you're proposing a new algorithm that is simpler than the existing algorithm, it's of course different. But let's assume the standard case that you modify the algorithm to be a little bit more complicated, and you want to propose, oh, this algorithm that is a little bit more complicated, I want to use it. In that case, there is a cost for using the algorithm. So you should ask yourself, is the benefit worth the cost? What is the benefit that would make it worth using my new algorithm? And that will indicate for you what should be the meaningful difference. Okay? All right, let's go to the next question. The next question from the student is, I wonder why the alternate hypothesis of the steel rod problem is mu1 smaller than mu2 and not mu1 different than mu2. That's a very good question. So this is actually a little bit similar to the answer to the previous question. In the steel rod design, if you remember, we said that the engineer was proposing a new method for cutting the steel rods. So because it's a new method, we assume that there is already an existing method that is already used on the factory. The machines already use this standard method. So to start using a new method, it has a cost. And because it has a cost, we are only interested in using the new method if it's better. We're not interested in using the new method if it's worse. So because of this, we are not interested to know if the methods are different or not. We just want to know if the method is better or not. So we use mu1 is smaller than mu2. On the other hand, if we're just studying the algorithms and we are interested if they are different, not only if they are better, but also if they are worse, then we might want to use a two-tailed test in that case. Okay, the next question is more about the class itself. So one student said that it's hard to understand the materials because Japanese statistic terms are very different from English ones. So the student was asking if they should read the Japanese material beforehand. And I found this to be a very interesting question because I did not actually know that the Japanese statistical terms were so different from the English ones. I think we could talk about that in the next office hour and you can show me some examples and we can talk about it. My intuition is that if you study the Japanese terms carefully, you may see that they are might be similar because the mathematics is the same underlying both of them. But in that case, if they're really different, I would maybe recommend that you should study the basic terms in English, not in Japanese, because when you're going to publish your paper in international conferences, you want it to reach on many different people as possible. So to increase the reach of your research, you should use maybe the basic statistical terms in English. But let's talk about that in the next lecture. And if you have any questions about basic statistic terms that you are not familiar with, feel free to ask because I will be happy to answer them by email or on Manaba or here in this survey questions. Okay, the final question was one student that suggested that the feedback comment video should be the first video of each week. This is an interesting idea, and as you can see, I'm doing this week. I'm not sure which one is better. As you said, it makes sense if the comments from the last week come first. But my goal for this lecture in the long term is that when I'm satisfied with some of the videos, I do not change them. I use them the next year again. In that case, if the content videos are fixed, but the feedback videos are always different, maybe it would be better to have the feedback videos in the end. I don't know, but I will try to put the feedback videos in the beginning, being video number 0, and tell me if you like this change. All right, this was the last question. So I will just remind you that the comments about the reports will come in a future video. And in the next video, we are going to have a R tutorial and a case study using R. Thank you and see you next.